And I'm very pleased to be able to introduce Shun Karato, who many of you know. Shun, a little bit of his background for those who aren't familiar. Shun got his PhD at the University of Tokyo. He was a research fellow at Australia National University, and then he was a professor at Minnesota for many years. And then he finally moved to Yale in about 2001. So for the past 20 years, he's been at Yale. Shun has an extremely long list of awards and prizes. I won't mention them all, except in a few years back, he won the Ing Lehman Award from AGU. Shun has been long a pioneer in rock deformation, things like the effects of grain size, water, partial melting, pressure on rheology. He's made fundamental contributions to the links between deformation and the development of preferred orientation and implications for seismic anisotropy and consequently dynamics. He's made major contributions to understanding seismic wave dispersion and attenuation. And he's been a leader in understanding the effect of water in minerals that are nominally anhydrous and how that affects their rheology, deformation, electrical conductivity. He's made major advances in how water is stored and exchanged between the surface and the deep earth. And his research extends all the way down to the inner core, where he has examined the evolution of the inner core over time and its deformation behavior. So without any further ado, I'll turn it over to Shun. Let me get your title here. It's Synchrotron in-situ experiments and their relevance to mantle rheology in earthquakes.
Thank you very much. I'm trying to find my file. Okay. Well, thank you very much for number one for organizing this very important workshop, but also invited me to give a talk on rock deformation. So yeah, I'm going to give you an overview kind of talk on what we should do or we can do using synchrotron deformation of rock deformation, which may help improving our understanding of Earth in time. And I'm going to give a very broad talk, and my colleague Jennifer Giraud, she will be given more focused detailed talk on deformation. The part of the work which I'm going to present is based on collaboration with many colleagues in my group. But also, I must mention that I was very slow in using synchrotron until Don Widener told me, Shun, you must use this. And then he invited me to the NSLS a couple of times. And then finally, I was convinced, okay, that's great facility. And everything I used in the synchrotron is done by Don Widener about deformation. And also the synchrotron deformation experiments were helped by beamline scientists like Heian Chen. Okay, thank you very much. And so this is the outline and the summary of my presentation. And first, I should mention, rock deformation studies have obvious implication to many of the issues which are listed in Earth in Time, which we discussed before. Suki Dorfman, she mentioned 4 items. I can list 7 out of 12 related to rock deformation. And obviously mantle convection is rock deformation related, but the mantle convection issue is also related to another very important question in our science, which is chemical evolution. And also the rock deformation, of course, include the friction, earthquake, and earthquake friction, of course, related to the fracture and the societal issue of mitigating the damage. But also, as I'm going to briefly mention, as understanding earthquake friction dynamics is very closely linked to the question of why plate tectonics works on Earth, not on Venus, for which I have a couple of papers on it. And another very important concept, which I'm going to emphasize several times, is that there are very important differences between elasticity or equational states, so to speak, equilibrium properties and rock strength. Elasticity is more or less equilibrium property. Anisotropy, some people sometimes emphasize, but it's very small compared to anisotropy in rock strength. And heterogeneity, mineral A mixed B mixture, yeah, elasticity is different but small. Anisotropy in plastic deformation can be as high as 1,000 times from mineral A, mineral B, or direction A, direction B. Similarly, the heterogeneity is very large. And also very fundamental concept behind rock deformation is it's not an equilibrium property. And strength of rocks depends on internal variables, not only just the external applied stress, such as internal stress or geometry of asperities. Many of them evolve with strain, okay? So these are really fundamental difference between elasticity and rock strength. And many of those unique questions about related to rock deformation, which I summarized above, can be addressed by synchrotron deformation, but not conventional approaches. Okay, let's see. And so this is the list of 12 issues as in time, including magnetism, plate tectonics, etc., etc. Among 12. Let's see. Yes, I can point out the several issues which are very closely related to rock deformation, of course. Plate tectonics and critical element distribution related to mantle convection, and of course, earthquakes, and the volcanism is related to the motion of materials, as well as the low temperature to high temperature, and the water transport, and water cycle, deep water cycle, and of course the natural hazard, of course earthquakes, and as far as the geodynamo is controlled by the mantle is the master and core is a slave. So in this connection, yes, rock deformation studies also have important implication for geodynamo. So this is a cartoon showing the whole Earth, and rock deformation studies have lots of potential impact to understand mantle convection. For example, either convective patterns are more or less uniformly distributed or localized deformation, and also the earthquakes which occurs in the shallow part. And those are issues which rock deformation studies can address. And the key questions in rock deformation, which are linked to the important geophysical issues, are summarized in here. In terms of mantle convection, obvious, but a very important question we need to address is the depth dependence of rheological properties. Deformation experiments are easy at shallow conditions. Hundreds of experiments are done, but at high pressure conditions, experiments are extremely challenging, but we have made many progress. So the effect of high pressure. And another issue about the plastic deformation is, as I just mentioned, rheological properties are not the equilibrium properties. Rheological properties evolve with deformation. And evolution of strengths is very closely linked to the possible shear localization, which has a tremendous implication for material circulation. Also, the strain dependence of rheology brings another important question of transient creep, steady state creep. Steady state creep, more or less steady state deformation is what we are interested in terms of mantle convection. However, what geophysicists tell us about Earth's rheology from geophysical data analysis include really small strain, like elastic strain. So the connection between transient creep and steady state creep is an important question to be addressed in terms of mantle convection. Regarding earthquakes, earthquakes are unstable fault motion, okay? And the question related to earthquakes are, for example, under which condition unstable fault motion occurs? And how unstable fault motion occurs? Related to those questions, a few issues are obvious, which can be addressed by synchrotron. One is the earthquakes are unstable fault motion. So we have to address stability of the fault motion, and stability of fault motion is very sensitive to the pressure. However, the previous rock friction experiments are done only at very low pressures, less than 100 MPa, not GPa, 100 MPa. Okay? And again, the stability or instability of friction really depends on tiny modifications to the fault properties. And the previous studies are not in situ measurements, so they did experiments of friction and found unstable deformation, and the by ex situ observations, they found probably the cause for unstable deformation is such. With the synchrotron experiments, we can improve understanding of those processes. So this slide, I summarize some of the uniqueness of the rock strength as compared to elasticity. As I mentioned earlier, elastic constants is the related to macroscopic stress and strain, and then elasticity is a property of material itself. Depends on pressure, temperature, and composition, but it's nothing to do with the history. In contrast, rock strength deformation, plastic deformation or friction are very sensitive to internal structure or conditions of the materials, not only just by applied macroscopic stress. For example, for plastic deformation rate is, of course, dependent on applied macroscopic stress, but the internal stress plays also very important role in contrast to elasticity. And in case of friction, the experimental results show shear stress needed to slide the fault is proportional to normal stress, and the coefficient is called friction coefficient. However, the detailed studies show that friction coefficient is approximately constant, but it is a function of velocity of fault motion and displacement. So the main point is the rock strength, either plastic flow or friction, those properties are sensitive, not only macroscopic imposed conditions, but also internal stress or conditions in the sample itself. That can be characterized by only synchrotron, but not by classic deformation experiments. So in this slide, I'm going to show contrasting aspects of the classic conventional deformation experiments and synchrotron deformation experiments. In the conventional deformation experiments, you have your sample under certain conditions and apply the force from outside, and then measure the force by load cell. This is applied stress, and then measure the displacement, and then you can define the how your sample deform against macroscopic stress, and then you can measure the macroscopic strain rate. A few points. With this kind of design, extending this kind of experimental technique to high pressure is very hard because it's very difficult to apply large stress to a sample under very high pressure conditions. But also you can see connection between macroscopic strain or strain rate and macroscopic stress, but you don't know what's going on in your sample. In synchrotron deformation experiments, several factors are quite contrasting to the classic conventional deformation experiments, synchrotron facilities, and then you can bring something like this equipment, which I designed, rotation trichomer, tiny sample is here, and then you put X-ray through your sample, and then measure the geometry change of your sample, as well as you collect diffracted X-rays from your specimen to analyze stress. For example, this is the Don Widener's design. Sample is over there, X-ray comes here, and then you collect the image to determine this strain, and then you collect diffracted X-ray using white beam to estimate stress conditions. So stress in the synchrotron experiment is determined through the diffracted X-ray inside of your sample, not by the force applied from the exterior. So you are going to determine stress inside of the sample itself, which is completely different from the classic deformation experiments. And theory is developed 2009. I wrote a paper on it, how you estimate stress from the diffracted X-ray as a function of various orientations. And the main conclusion is diffracted X-ray shows the deformation of lattice spacing depends on the angle at which diffracted X-ray is collected. And so therefore, it depends on the displacement depends on the angle. And from which you can determine essentially strain along certain directions. And then if you know elastic constant, strain using elastic constant, you can calculate the stress. However, the calculated stress, according to theory, not depends on elastic constants, but also the viscous anisotropy, plastic anisotropy of the grain itself. That is a very important factor in terms of the synchrotron deformation experiments. So in synchrotron deformation experiments, we determine microscopic stress because of the X-ray diffraction. And that is very important because microscopic stress defined by this way depends on plastic anisotropy. So therefore, not only just strength, we can determine plastic anisotropy from the synchrotron deformation experiments. And because diffracted X-ray is collected from your sample, if your sample has 2 or 3 more different minerals, you can determine the stress acting on each mineral, which you cannot determine with classic technique. Okay, and because X-ray is very focused and very high intensity, it can be put through your sample. So the application to high pressure condition is much easier than the classic conventional approach. So let me talk about a little bit about the transient versus steady state creep, as I mentioned earlier. Very powerful technique to infer viscosity distribution of the Earth's interior is to analyze time dependence of the sea level after the melting of the glacier. This is post-glacial rebound. Everyone learns this physics to see how we can infer viscosity versus interior. But amazing and embarrassing fact is this deformation involves extremely small strain. You can very easily estimate order of magnitude of strain by dividing vertical displacement by horizontal scale using definition of strain. Vertical displacement maybe 10 meter, 100 meter, but the horizontal scale is 10,000 kilometer. So the strain is 10 to the minus 5. You can easily estimate the elastic strain associated with this kind of phenomenon, which is about 10 to the minus 4. So the very clear conclusion is strain involved in post-glacial rebound is elastic strain or less. Then you should ask, wow, is the viscosity corresponding to so tiny strain is similar to the viscosity at steady state conditions, such as mantle convection? Answer is clearly no. And so it's very important to address the question of steady state versus transient creep. And this slide shows one analysis of the transient to the steady state creep evolution associated with strain accommodation. Brief summary is, when strain is so small, mineral deforms and here and there, and then there's the incompatibility. If strain is so small, incompatibility can be accommodated by elastic deformation. If strain becomes so large, elastic deformation is not enough. So you need to invoke the plastic deformation. So therefore, as strain goes small to large, there should be transition from transient to the steady state viscosity. This is what we like to understand in terms of mantle convection. However, if you do this analysis, you can calculate what is the threshold strain from transition to the transient to the steady state deformation. And based on the simple theory, you can predict critical strain is roughly order of elastic strain. If strain is smaller than elastic strain, like a post-glacial rebound, deformation is controlled by soft, easy slip system in your mineral. If deformation is steady state, deformation is controlled by hard slip system. And if you look at the deformation of olivine, for example, soft and hard system has a very different strength. And more interestingly, water content sensitivity is very different between two regimes. So therefore, it is very important to understand what is the behavior from transient to steady state creep. This can be done by synchrotron deformation experiments, which I think Jennifer is going to show later. The reason why you can address this is in synchrotron deformation experiments, we can measure the lattice strain for different diffraction planes, and then results show different magnitude of stress depending upon the HKL, which indicates the plastic deformation is anisotropic. And then when you compare these scattered stress estimates as a function of strain for your specimen deformation, and if you have a stress sensor in this particular experiments, stress sensor gives the average stress of your sample by this solid line. And you can see that when strain is small, the macroscopic stress acting on your sample is near the weaker strength. However, as you go to steady state, it is close to the hard slip system. So this is the one example to show the controlling process changes from soft slip control to hard slip control as strain goes over elastic strain. This is elastic strain. Two-phase deformation, let's see, is another very important geodynamic issue. And particularly, this is important for lower mantle. Lower mantle is, roughly speaking, made of 70–80% of bitumenite and 20% of ferropericles. Interestingly, 20% of the phase is weak, and then matrix is very strong. If situation is opposite, matrix is weak, and tiny one is the strong, who cares? Okay, the deformation is always controlled by matrix. However, if volumetrically small phase is much weaker than volumetrically dominant phase, interesting thing could happen, okay? And a few points. In terms of elasticity, seismic wave velocities, ferropericles and bitumenite velocities are not so different. That's why we have been debating composition of the lower mantle based on seismic velocities. However, the creep strength or viscosity of ferropericles and bitumenite are quite different, not 10%, no, 100 or 1,000 times different. That is a unique part of plastic properties. Plastic properties can be very different between coexisting minerals. So therefore, if you have a 20% weak phase and deformate, deformation might be controlled by weak phase. Imagine 20% of liquid. When you have a liquid, 20% strength of rock is 0. Okay, so this is a very remarkable issue of the lower mantle. And there was a classic work done by Blumenfeld and Kobe Clamp using classic deformation experiments of calcite and sodium chloride mixture, and they deformed the mixture to some strain and stop experiments, cut the sample, look at the interior, stop experiments, cut the sample, stop, cut, stop, cut, stop, cut. And then they did a very nice analysis of the strain distribution between two phases, and they found very fundamental, important fact. When strain is very small, the deformation occurs more or less sodium chloride and calcium, same strain to begin with. However, as strain goes up and up, stress constant, homogeneous stress conditions slowly evolve to a nearly homogeneous stress. Then as you can imagine, if condition is nearly homogeneous, then weak phase deforms a lot and the strength is controlled by weak phase. However, in contrast, if strain is homogeneous, yeah, then the control is opposite. So this is a nice experiment, but this was done classic way, but cut and stop and cut, stop and cut. We can do a similar thing by synchrotron, and I show you the one example from my lab on the lower mantle assembly. Yeah, this is the actually starting material is olivine, and we transform olivine to bridgemanite and a magnetic boostite mixture. And we are able to do deformation experiment in simple shear rotational experiments at 27 GPa and roughly 2,100 Kelvin. This is the melting temperature. T over Tm is about 0.75. This is remarkably high, okay? Even higher than typical lower mantle, upper mantle deformation experiments. The strain rate is 10 to the minus 5. So these are really typical low pressure, similar to low pressure experiments. And because of synchrotron, we are able to measure the stress of the acting on MgO and bridgemanite at the same time. And we show bridgemanite is much stronger than MgO. And also we see hint of weakening because error bar is so large. I'm hesitating to push too much, but you can see microstructural evidence suggesting weakening could occur because you can see, isn't it amazing? MgO looks like a fluid. This is MgO, this is bridgemanite, okay? So ferropericles deforms like a liquid. Yeah, this is the remarkable results, but this is very preliminary. Error bar is very large because X-ray was so weak in this particular case. So we really have to extend this to much larger strain and much higher resolution. Error bar is really too large. Let's change the subject to the brittle deformation, faulting and earthquakes. Why do we care about brittle deformation? A couple of reasons. Of course, brittle deformation is related to the earthquakes, and everyone wants to understand why earthquakes occurs and how does it occur. But also, strength of the rocks in a brittle regime, at least in my theory, has an important contribution to determine either plate tectonics can occur or not. So it's a big picture mantle convection issue, but it's more earthquake-related issues. And earthquakes are unstable fault motion, and you should ask, oh, fault motion is stable, under some conditions, but unstable under different conditions. What determines this? So that is one question you can address. Yes, when brittle deformation occurs, finally fault is formed, and then deformation occurs along the fault. So we focus on fault, the friction. And for friction, couple of concepts. One is, if you look at the slow friction coefficient at a slow velocity, there's a remarkable general rule called Bayer's law. Friction coefficients are universal constant, doesn't depend on rocks, and doesn't depend on temperature at all. And it's 0.6. This can be explained very easily by very simple model of asperity. However, if static friction is everywhere, number one, you cannot make plate tectonics because strength against brittle failure is so strong. However, if you can reduce, if you have some mechanism to reduce strength at the friction coefficient from 0.6 to say 0.1, simply you can rotate this line to 0.1, then strength of the lithosphere is low enough to make plate tectonics. So if there's a mechanism of reducing friction from 0.6 to lower level, that would help explain the plate tectonics. And also, this will help how earthquakes occur and what is the friction coefficient associated with earthquakes. And breakthrough in terms of understanding this behavior occurred based on the contribution by Toshi Shimamoto. He designed everything and he got all sciences. He developed the friction equipment to allow study the friction at high velocity by rotation. Okay, rock specimen is rotated relative to the another by rotation. Then he investigated the friction behavior as a function of friction velocity. If friction velocity is as slow as plate tectonic velocity or a little bit higher, the Bayer's law works. So the friction coefficient doesn't change, like 0.6 or 0.7. However, if friction velocity, slide velocity goes to order of 1 meter per second, then friction coefficient drops substantially. This velocity is corresponding to the fault velocity associated with the earthquake fault propagation. However, another very important observation in terms of weakening from high friction to low friction based on the unstable fault motion is friction coefficient doesn't change from high to low instantaneously. Rather, friction coefficient changes gradually from initial high value to low value. The reason for this is that to reduce the friction coefficient, you need to modify the structure of the fault plane, particularly melting. And as you can see, in order to make melting, you need to do some work. So work cannot be done instantaneously, so it takes some time. And as you can imagine, well, two important things you can see. That is unstable motion to get the very low friction coefficient, that is earthquake. And earthquake type fault motion occurs not instantaneously, but gradually. This means that before an earthquake, there must be some precursor associated with change in fault structure. And number two, if this slow instability is related to the work, there must be high pressure dependence, because if pressure is high, you have more work done. So this kind of instability is easier. Okay, so you expect high pressure effects.
1 minute.
Yeah. However, the previous work done by conventional equipment, so the maximum pressure to investigate this was 50 MPa. With the new type of equipment, we should be able to extend this to much higher pressure. That should be the very important goal for future work. And those microstructures shows melting is a cause for reduction of friction. And this is nice work to see the evolution of asperities by Dietrich and Kilgore. We should extend this to an in-situ observation of the structure of the fault plane by conducting something like this equipment, the experiments, rotation along the fault plane, put it into at high pressure conditions, and bring it to the synchrotron facility. You can watch what's going on during the fault motion by synchrotron imaging. That will tell us a lot about the structure change associated with instability. So this is a summary of my talk, which I showed it before. There are lots of questions we can address in connection to us in time from rock mechanics point of view. One is mantle convection, and another is the friction. Friction part has not been talked about in connection to synchrotron, but using capability of in-situ observations during like a sliding, I hope that we can learn a lot about what's going on through the unstable fault motion, which can tell us processes of earthquake deformation and related to the other issues, such as plate tectonics. Thank you very much.
All right, thank you very much, Shun. We have only brief time for a question or two. All right, well, let me make something that's maybe more of a comment. I mean, I think you did a nice job of showing the important questions and the distinction between elasticity and rock strength and the very complicated nature of rock strength, the evolution or history dependence. You know, that one could look at that in a negative way and argue that your laboratory experiments are very different than the Earth. You know, your lower mantle experiments are much simplified relative to the Earth, and because of the complexity, the history dependence, it's a really hard thing to really be sure you're relevant to the Earth. I mean, you don't know the grain size, the water content, you don't really know the composition. So you know, I think there's a negative way to look at that as well. So I'd be interested in your comment on that.
Oh yeah. Well, that's an excellent point, which is what I'm always thinking. The answer is scaling analysis. You must apply scaling analysis, half based on theory and half based on your limited experimental data. Then scaling analysis. And a very powerful way to do this is the constructed deformation mechanism map.
Okay, great. And can you also then add a comment on, you know, your focus is almost entirely on theory. What about, I mean, on an experiment, what about the role of theory? In particular, I'm thinking about MGO, where there has been some theoretical calculations of diffusion and such that are probably in good agreement with some of your results, right?
Oh yeah, there, of course, yeah, there are some aspects that theory can contribute, but also there are some aspects that only theory can address. For example, we are learning two-phase mixture deformation lower mantle, and we can investigate in the laboratory how two-phase deformation occurs. But if you go from there to mantle convection, you need a large-scale theoretical calculation, which we are doing. Yeah. So there are several things. Yeah, theory is also important.